In today's section, we're going to study rhombuses, rectangles, and squares. And the objectives of this section are to use properties of size and angles of rhombuses, rectangles, and squares, and to use properties of diagonals of rhombuses, rectangles, and squares. So in this lesson, we will study three special types of parallelograms: rhombuses, rectangles, and squares. And let's see the properties of these special parallelograms. Let's begin with the rhombus. A rhombus is a parallelogram with four congruent sides. A square is also a parallelogram that has four congruent sides and something else, four right angles. And a rectangle is a parallelogram with four right angles. Here we have a Venn diagram that shows the relation between parallelogram, rhombuses, rectangles, and squares. Each shape has the properties of every group that it belongs to. For instance, a square is a rectangle, is a rhombus, and is also a parallelogram. And it has all the properties of those shapes. So a square, it has the property of the rectangles, and the rectangle, the main property of the rectangle is that is a parallelogram that has all the angles measuring 90 degrees. And also it has the properties of the rhombuses. The rhombus, for the definition, it has four congruent sides. So the square has the property of both. It has four right angles and it has four congruents. Let's make an example. In this example, we're going to describe a special parallelogram. So we're going to make a decision whether the statement that is going to be given is always, sometimes, or never true. We're going to have three sentences, and the first one it says a rhombus is a rectangle, and the second one it says a parallelogram is a rectangle, and in the next one a square is a rhombus. So let's begin with the first one. Is a rhombus a rectangle? If we look at the figure above the Venn diagram, we can see that in the figure, in the Venn diagram, we have some oval representing rhombuses, another one representing rectangles, and they overlap. And the region that they overlap is the region for the squares. So a rhombus is a rectangle always, sometimes, or never. And I think that you can see from the figure that the answer to this is that is sometimes true. A rhombus would be a rectangle only if it is a square. A parallelogram, B. A parallelogram is a rectangle, and you can see that at the top of this Venn diagram we have the classification of parallelograms. It says parallelogram, and the parallelograms are divided into rhombuses and rectangles and squares as well. So a parallelogram is a rectangle, not always. So like the previous one, it is sometimes true. When is going to be a parallelogram a rectangle? When the parallelogram has all the angles congruent, and beyond that, the angles are also, that each angle measures 90 degrees. And the last one, a square is a rhombus. And if you see the figure, you can see that the figures representing the rhombuses and the rectangles overlap. And in that overlapping, it is being labeled with squares. So that's the part in common for rhombuses and rectangles. So the question is, a square, or the sentence, a square is a rhombus? And the answer is yes, always is true. A square shares the characteristics of a rhombus. And the main characteristic, that is the rhombus, it has four congruent sides, and a square has four congruent sides. And something else, that all the angles measures 90 degrees. But to be a rhombus, a square, the only needed condition is that all the sides measure the same. So it's always true. Let's make a second example. And here we're going to use properties of special parallelograms. And let's see, we have this quadrilateral ABC that is a rectangle. And the question is, what else do we know about this rectangle ABCD? And as you can see, and it's really clearly stated in the figure, it has 4 right angles, and this is the definition of a rectangle. The definition also states that rectangles are parallelograms. So this quadrilateral ABCD has all the properties of parallelograms. And these properties are the following. Opposite sides are parallel and congruent. Opposite angles are congruent. Consecutive angles are supplementary. That means that they add up to 90 degrees. And the diagonals bisect each other. Let's make an example 3, and in this case we're going to use the properties of a rhombus. Here we have the rhombus PQRS, and in this diagram we need to find the value of y and also what is the length of each segment. I know by definition that if a figure, in this case PQRS, is a rhombus, all the sides must be congruent. So that's what we are going to use in here, and since we have the two sides PS and RS with some labeling, I see that for the PS the expression represented the length of this is 2y plus 3, and for the segment RS the expression representing the length of this side or segment is 5y minus 6, and I know by definition that this must be they measure the same because all sides are congruent. So what we can do here is to write an equation with this. So the equation is 5y minus 6, it would be equals to y plus 3. And what I need to do now is to solve this equation. So when we start solving the equation, we can make the decision to put the numbers together on one side. So we need to get rid of the negative side from the left side. We add 6 to both sides, and the equation becomes 5y equals to y plus 3 plus 6, that becomes 9. 5y equals to y plus 9. Then we need to make another decision and put together all the variables on one side. So this becomes 5y minus 2y, that is 3y, equals 9. Finally, to leave alone the y that is being multiplied by 3, we need to divide both sides by 3, and the value of the y equals 3. Then you can see in the figure, in the sentence, they are asking us to find the length of each segment. And let's begin with the length of the segment PS. I know that the expression representing the segment PS, the length of the segment is 2y plus 3. So in here I'm going to replace the value of the y that I just found, that is 3. And 2 times 3 plus 3 is going to give us 6 plus 3, that is 9. So the length of the segment PS is 9. And I know that the length of the segment is QR and QP is exactly the same. So they all measure the same. So just to prove that if I replace in the expression 5y minus 6 that represents the length of the segment as R is going to work, let me make the substitution. I know that the value of the y is 3. 5 minus 3 minus 6, it must be equals 9. 5 times 3 is 15 minus 6 is equals 9. So the length of the segment is R is 9. Therefore, the answer to this is that the length of each side is 9 units. Let's continue and let's see the diagonals in special parallelograms, in these special parallelograms. And here we're going to have some theorems about diagonals of rhombuses and rectangles. So let's begin with the first theorem that we have about this. A parallelogram is a rhombus if and only if its diagonals are perpendicular. In this figure that we have over here, that is a ABCD quadrilateral, and we can say the following in this quadrilateral. ABCD is a rhombus if and only if the diagonals AC and BD are perpendicular. If you notice in this theorem, they use the connector if and only if. That it means that this is a biconditional statement, and out of each biconditional statement we can get two sentences. The conditional statement it's converged. So if we split this theorem in two parts, what is being stated stated is the following. If a parallelogram is a rhombus, then its diagonals are perpendicular. That would be, let's say, the conditional statement. And what would be the converse of this? That is also true. If the diagonals of a parallelogram are perpendicular, then we can conclude that this parallelogram it is a rhombus. And let's continue with the diagonals of special parallelograms. So here we have a second theorem. A parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. So here we have this quadrilateral ABCD, and ABCD is a rhombus if and only if the diagonal AC bisects the opposite angles DAB and BCD, and also if the diagonal BD bisects the angles ADC and CBA. And again, since we have this theorem stated like an if and only if, it is a biconditional statement out of which we can get two statements that are going to be true. If I have a parallelogram that is a rhombus, then each diagonal bisects a pair of opposite angles. And if I take the converse of this, if each diagonal of a parallelogram bisects a pair of opposite sides, then guarantee that this parallelogram it is a rhombus. Let's make another example. GHJK is a square with diagonals intersecting at the point L. Given we have that GH is 2, GL is equals square root of 2, and what we need to do is to complete each of the following statements. We need to find the length of the diagonal HK. We need to find the measure of the angle KLJ. We need to find the measure of the angle HJG, and also we need to find the perimeter of the triangle HJK. So before we answer these questions, let's see the figure that is given, that is a square. I know that a square it is a parallelogram, and I also know that a square is a rectangle. Let's keep this in mind. When we have a parallelogram, we know that the diagonals bisect each other. The diagonals here are GJ and KH. Also, since a square is a rectangle, I know that the diagonals are congruent. Is one of the properties that we have in a rectangle. The diagonals are going to be congruent. Therefore, all these segments that are formed after intersecting the diagonals G, J, and KH are going to be congruent. So I have this marking here, these sides are congruent, and therefore each one of them measures square root of 2. KL, the segment KL measures square root of 2. The segment J measures square root of 2, and also the segment LH measures square root of 2 units. Also, I know that this quadrilateral GHJK is a square, it's given, so all the sides of this square must be, the sides that make this square are gonna be congruent. So HJ is congruent with GH, also JK is congruent with GH, and also KG is congruent with HG, meaning that all these segments that we just mentioned measure 2 units. Also, since GHJK is a square, each of the angles of this figure measures 90 degrees. So the angle KGH measures 90 degrees. The angle GHJ measures 90 degrees. The angle HJK measures 90 degrees, and the angle JKG measures 90 degrees. Also, using another property of the rhombuses, the diagonals bisect, each diagonal bisects a pair of opposite angles. So the diagonal JG bisects the angle KGH and the angle HJK. And also the diagonal KH bisects the angle GHJ and the angle JKG. So we have all the marking in the figure. and we're ready to find the information that we have in here, that we are being requested. What would be the length of the diagonal or of the segment HK? I noticed that the segment HK, it is formed by the segments KL and LH. So I need to add these two pieces to get the length of the segment KH. And I noticed that the length of the segment KL, it is square root of 2, and also LH is square root of 2. So if we add them together, what we get is 2 square root of 2. When we add radicals, we add the coefficients, and we keep the radicals. So 1 square root of 2 plus 1 square root of 2, it will be 2 square root of 2. What would be the measure of the angle KLH? I notice KLJ, sorry. I notice that this angle, it is a vertical angle with the angle GLH, and the angle GLH measures 90 degrees. Therefore, because vertical angles are congruent, this angle measures 90 degrees. If we go a little bit beyond, also the angles GLK and HLJ will measure 90 degrees. And what is the measure of the angle HJG? Okay, the angle HJG is one of the angles that was bisected by the diagonal JG, and since the angle HJK measures 90 degrees and the diagonal bisects this angle, the diagonal AGJ, it means that this angle is half of the measure of the angle HJK, that is 90 degrees. Therefore, this angle measures 45 degrees. In the figure, we have all these angles that were obtained as a result of the bisecting of the diagonals. Every single angle of those measures also 45 degrees. And what would be the perimeter of the triangle HJK? Let's see. This triangle, what we need to do is to add, that's the definition of perimeter of the three sides of the triangle. I need to add the perimeter, I need to add the length of the sides HJ, that is 2. I need to add also the length of the segment JK, that is 2. Also, I'm going to need to add the length of the segment KH, and that segment measures it will be the sum of the sides KL and LH. So that's why I'm going to add KL measures square root of 2 and LH measures square root of 2. So we add all these together, and the answer will be 2 plus 2, that is 4, and square root of 2 plus square root of 2, that it will be 2 square root of 2. So the perimeter of the triangle HJK, it is 4 plus 2 square root of 2 units. Let's continue with the diagonals of special parallelograms. Here we have a rectangle, and the theorem says the following. A parallelogram is a rectangle if and only if its diagonals are congruent. So, in the figure, ABCD is a rectangle if and only if the length of the segment AC, it is congruent with the length of the segment BD. AC and BD are diagonals. And once again, this theorem is stated in the if and only if form, meaning there's a biconditional statement, and out of a biconditional statement we can get a conditional statement, and it's converse. So if we put this theorem in this way, it will be we will have the following sentences. If a parallelogram is a rectangle, then the diagonals, its diagonals are congruent. And if we take the converse of this, if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. We have an example 5. We're going to do a checking of the figure that we have in here. We're going to check if this figure is a rectangle. And we have an application in carpentry. We have the following. We're building a rectangle frame for a theater set. And first, we put together the 4 pieces of wood as is being shown at the right. And the question is, what is the shape of the frame? To make sure that this is a rectangle, we are going to measure the diagonals. And it happens that when we measure the diagonals, one of them is 7 feet and 4 inches, and the other one is 7 feet and 2 inches. And the question is this frame a rectangle? And we need to explain. Okay, first of all, I want you to notice that the length of the opposite sides are 4 feet is one pair of opposite sides, and the other pair is 6 feet and 6 feet. So this figure is a parallelogram. No problem with that. But the question here is, it goes beyond, and the question is this figure a rectangle? And we have the question here. The diagonals measure 7 feet and 2 inches, one, and the other one measures 7 feet and 4 inches. If you notice, these values are different by 2 inches, and therefore, this parallelogram is not a rectangle. If it were a rectangle, the diagonals would be congruent, something that didn't happen in this example. And this is the end of the explanations of this section that is called rhombuses, rectangles, and squares.